Hey there, Year 12. So in this video now, I'm going to be talking about how can we avoid doing a recurrence over and over and over, and say if I wanted to work out for 10 days, how would I do that? Now, very similarly to your recurrence and financial modeling that you did in the past, so I'm going to use the same example I used in my previous video. So say V0 is 8,000, and then I said Vn plus 1 was equal to, let's say, 10% extra, so 1.1 multiplied to Vn, okay? Then, in your calculator, this is how we would have done it, okay? So I'm just going to clear this out for now. We would have done 8,000 to start off with, and then back in that previous chapter on recurrence and financial modeling, you would have done times 1.1, and you keep pressing enter 10 times. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If you want it 10 days or 10 years. Okay, now there was a shorter way that you learned in recurrence formula, is that because you're always timesing or multiplying by 1.1, the formula changes. Instead of writing it like this, we can write a rule to represent this, and we can say V of n, so it could be any nth year that you want. Instead of 0 and then n plus 1, we're going to call it Vn now. Vnth rule will tell you that it is 1.1 to the power of n, because it's repeated multiplication. If you do 1.1 times 1.1 times 1.1 times 1.1, this can be written as 1.1 to the power of 4. This is why the rule, when you're multiplying this repeatedly, is going to be to the power of n, and then it's times Vn. So it means that now, if I wanted to find out the 10th day, I can just simply write in, as an example, I can do V of 10, which is 1.1 to the power of 10 times V0. Sorry, V0. There should be V0 there. Okay, and so I'm timesing it by V0, which is 8,000. So here we go on my CAS. So remember before, let's see how many times I did it. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so that was 10 times that I had to do it recursively, right? Now I can do it all in one go. I can do 1.1 to the power of 10. Actually, I should put in brackets. 1.1 to the power of 10, okay? Multiplied to the starting value, which was 8,000. And can you see I didn't have to do it recursively, and both the two answers there are exactly the same, the top and bottom, yeah? So you can see this is a shorter way, and hence it's a rule that allows you to do things without doing it recursively, right? Now, similarly with matrices, they are the same idea. Notice that it is the recursion. This is the recursion here. It is T, transition matrix, multiplied to Sn. So when you're multiplying, there's going to be repeated multiplication. Each time I did it, I have to times it by T. So instead, notice that they changed it to T to the power of N, because it's following the same idea. If you're going to do matrix, transition matrix times transition matrix times transition matrix times transition matrix, you can write all that as T to the power of 4, and that will be day 4, right? So this is where it's interesting. How can we calculate what we did prior? So remember when I was doing this example, we had to do it recursively. 1, 2, 3. I had to times T to S0, and then T again, and then T again. Notice how many times I multiplied T. Times T, times T, times T. It's T to the power 3 to get me to this day 3, right? So let's see if I can beat that by doing this now. So I'm going to go back, and remember I had defined S0 as this, and I had defined T as this. So that's my transition matrix, right? Now, instead of doing it recursively 3 times like I had in this example, what if I followed that idea and I did T to the power 3 instead? So T to the power 3 times S0, because that's my starting value, true? This is what I'm going to get. Notice it's 53.16, and I get the answer straight away for 46.84. I didn't have to go through all these steps here to get there. See what I'm doing there? So T3 times S0. So remember S0, all I'm doing there is I'm just doing transition matrix multiplied to S0. But remember, transition matrix is to the power of 3. That's what I'm doing there. Okay, so to the power of 3, this is the nth rule. And you can see that's how I got my answer. So I'm just going to copy this just so that you understand what we're doing here. I'm just going to copy that to illustrate my point. We could have done that previous example, day 3, if we were to find day 3 in one go. Now, in our particular example, I'm probably just going to paste it over here, actually. Let me just paste it somewhere, just to illustrate my point. Okay, so in this particular example, you now want exactly the same thing, starting off the same 80-20, transition matrix is still the same, but it's after 10 days. Now, instead of doing it 10 times, okay, we're going to do it using the nth rule. Okay, so here I'm just going to write again just so that you can see. S0 was equal to 80-20. Okay, and we know that the rule was Sn plus 1 is equal to, and we would have had the transition matrix multiplied to Sn. Okay, so this is our transition rule, and we're already seeing that there had to be a shorter way of doing this, right? So here we go. I'm just going to illustrate the point again, and hopefully you see my what I'm trying to show you here. So we're going to do the same thing again. Let's say I did it multiple times. So I'll start off from the beginning. So how do we start it? We're going to say, let's label the starting matrix. So 80-20, that's my starting matrix. So S0, S0, so I've defined it. And then I'm going to use my transition matrix. Okay, so here's my transition matrix, 0.85, 0.05, 0.15, and then 0.95. Okay. And I'm going to store that as my transition matrix, which I'll call T. All right, now this is how you normally would have done it in the past. If you were to find the 10th day, you would have done T times S0, and that gives you 6931. Then you would have done T again times, so this is day 2, day 3, day 4, day 5, day 6, day 7, day 8, day 9, and then day 10. See what I'm doing? This takes a long time to do, isn't it? So that's my answer for 10 days. Alternatively, okay, so I'm just going to screenshot this to help you remember what I was doing. This is day 10. If we were to do that recursively, which is a long method. Okay, so I'm just going to put it over here to remind ourselves what we were doing. Over here. Okay, now there had to be a shorter way, and the shorter concept is to say, well, what if I just did, since I know I'm going to multiply t 10 times, why don't I do t to the power of 10, okay, multiplied to S0, which is the starting value. Let's see if it comes out the same. And can you see there, both answers are exactly the same. And I didn't have to go through it recursively to get there. Okay, so that's the point of the second part of the exercise. It's that you can shortcut this. Okay, I'm going to make this a bit smaller. I'm going to make this a bit smaller. So this is the recursion nth rule. Okay, so you can see here I'm using S0. This is S0. This is the nth rule. So they're saying it's t to the power of n. So remember the rule was Sn is equal to t to the power of n multiplied to S0. This is the rule. This is the nth rule. Okay, and I'm going to maybe just make that a bit smaller, and I'm going to move it over here. Okay, so this is the nth rule versus if you were to do it recursively, then over here, I'm just going to copy everything beforehand. So I got up to which one? 63.46. So starting from the very top, we had S0. Here we go, S0. So I just wanted to make sure that the working solutions is straightforward for you to see and understand the process here. So this is the starting value. I probably should make that smaller just to fit there. There's probably another one, so 47. Okay, there we go. I think it'll be up until this point. So you can see that I'm trying to show you here that we do it recursively, and it takes a lot of effort to go from this all the way down. See, that takes a lot of effort to get to that point. Actually, I should probably cover that. There you go. It's a bit ugly, but gets the point. There we go. So we had to do it day 1, day 2. So I'm going to write here, this is day 0, or day 1, sorry, day 1, because day 0 was up here. So this is day 0. This is day 2, day 3, day 4, day 5, day 6, day 7, day 8, day 9, and then day 10. Okay, you can see here, you can get straight away day 10 in one step. Okay, so this is the recursion. This is where you did S0 is equal to AT20, and then you did Sn plus 1 T times Sn. Okay, and that's the recursion. So over here, this is recurrence, but not the formula. This is the nth rule. Okay, two very different ones. So hopefully this video illustrates that point for you to understand the two, and that's how you work through them differently. And I tried to revise financial recursion over here. I'm just going to do this like this. Revision of recurrence and finance. Okay, but there you go. And then the last thing that you need to understand is what we call a steady state solution. Well, once we can use this S equals to 10 transition matrix to the power of n times S0, a steady state solution just means that in the long term, okay, in the long term, what would this turn out to be? There has to be obviously a point where it reaches an equilibrium. Okay, so when they talk about a steady state matrix, essentially they're trying to say, what if I continued that pattern on instead of 10 days? What if I continued it on to the 20th day? So you can see here, we started off at 60, 80, 20, yeah? We went to day 1, 69, 31, and then it keeps going. There's a lot of changes, but start to look at where is it sort of plateauing? See, notice the number of operational machines is now looking at the 30 zone quite a bit, isn't it? And then the non-operational is currently at 69, close to 70. So what happens if I went to 20 days instead? You see, instead of doing recursively 20 times, I can now use this rule and then work out 20 days. See, 20 days now leads me to 2574. What if I went to 30 days? Now you're starting to see something that's starting to plateau. Look at 20 days and 30 days. They're actually looking quite similar, don't they? It's like 25 will be operational in the long term, and then 75 roughly will be broken in the long term. So I can even try it by going up to 50 days, and you can see here that it is definitely plateauing at 25 and 75 for operational and broken, respectively. Okay, so this is what they mean by steady state, that there's usually at some point it starts to plateau. Okay, that's what they're trying to talk about. And often we just, to find out the steady state, what does it tend to, or what does the equilibrium state tend towards? you put in a large number. So in methods, I know we used to put it to 30. You can put it at 40 if you want, but generally 30 onwards is when it starts to plateau. Okay, so t to the power of 30 will give you a pretty good estimate. If you want, you can try 40 or 50. Okay, but I can clearly see that 25 cars were operational in the long term and 75 cars, machines. We were talking about machines. So 25 machines will be operational and 75 will be broken in the long term based on this percentage. Okay, so that's how you would do. I'm going to move it over here. I'm just going to write steady state to remind you what I did over here. So I would write over here steady state. This is the steady state. So here we go, steady state matrix. And this just means in the long term, you can expect 25 machines will be operational, and you can expect 75 machines broken based on the transition matrix they had started off with for us. Okay, and this is all assuming that the transition matrix doesn't change over time, that it stays the same. And that's one of the properties if you were doing methods that talk about that. But that's all you need to understand. So in the long term, which I would then recommend to use either 20, 30, or 50. In methods, we normally talk about 30, but I'd say 50, anywhere between 30 and 50 is a good number to test. Okay, so there we go. That's your steady state matrix. So if I were to do this example over here, it says estimating the steady state solution. You got your S0 as 50, 40. Transition matrix is 0.8, 0.1, 0.2, 0.9. Estimate the steady state solution by calculating for n. In this case, they tell you what to put for n. So 10, 15, 17, 18. So in my case, let's do it. Let's do an hour calculator over here. I'm going to start all afresh. And we're going to do steady state, which we start off with. Initial state was 50, 40. So I'm going to call that S now, S0. And then I'm going to put in my transition matrix. So transition matrix is 0.8, 0.1, 0.2, 0.9. And I'm going to now store it as T. And so we're going to try t to the power of 10, so the nth rule multiplied to S0. Okay, so remember you always have to multiply it transition to the steady the initial value. Don't swap it around, otherwise it doesn't work. So that's my 10th one. So I'm going to copy this down to see the 10th. Okay, so this is 10th. So this is calculating after 10 days or 10 years, whatever n represents. So here we go, we've got 10. I'm going to just copy paste that. They want us to try to look at what happens at 15, 17, and 18. So here we go. T to the power of 18 times S0. Oh, sorry, 15. They want 15. Here we go. So that's 15, 17, and then 18. Okay, so 15, 17, 18. So here we go. I'm going to copy this down and we're going to analyze that and then see what the long-term prediction would be. Okay, so here we go. I'm going to put it over here and then I'm going to make it a bit smaller just to see if it fits. Let's go. There we go. So we can now say this is for n equals 10, n equals 15, n equals 17, and this is n equals 18. So what we can see is that the equilibrium, we can see that if it's car rental, whatever's at the top, it plateaus at about 30. So we can say the steady state matrix or steady state solution. So right here, steady state matrix, you can expect it to be returned. So a number of cars that are being returned can be 30. Expected to be 30, whilst the other one is that looks like a 60. Oh, my pen died just at the right moment. Imagine I wrote 60 there. Okay. Yeah, the pen's dead. All right, but that should conclude my session for today, 30 and 60, and that helps you understand, if we zoom out a bit, that helps you understand how to do this exercise. So we've gone through how to do the recurrence relation with matrices. We looked at how to do the nth rule or the nth state, and then we looked at what a steady state solution is. Okay, so that hopefully gives you a better idea of how to do this, but that's the answer. So 30 and 60 is what you can expect, which adds up to 90, which makes sense because you had 50 and 40, which means that that was 90 cars to begin with. So you can expect 30 cars returned and then maybe 60 not returned, something like that. Okay.